So in this video we're going to solve for the impedance of a series circuit. So as you see here, we have a series circuit with a resistor, two inductors, and a capacitor. So and we're also given that the frequency of the circuit is 1 kilohertz. So we know that the impedance for a series circuit, we can calculate the total impedance Z, which is going to be the resistances plus J times the inductive reactance. So it's actually going to be, we have two of them, so it would be X of L1 plus X of L2 minus the capacitive reactance, which we just have the 1 of. Okay. So all we're doing is just adding these up. But remember that R is just a plain resistor, but we have the capacitive reactance and the inductive reactance. So the inductive reactance, XL1, is going to be 2 times pi times the frequency, so it'd be 10 to the third, times 0.07, right? This is millihenries here. And then for the capacitor, the capacitive reactance is going to be 1 over 2 times pi times 1,000, 10 to the 3, times 0.2 e to the minus, or 0.2 times 10 to the minus 6 for micro. Okay. And then we have the other inductor, which is 200 millihenries. So that would be X of L2 is going to be 2 times pi times 10 to the third times 0.2. And so if we calculate those then, so X of L1 becomes, so X of L1 is 439.82 ohms. 439.82 ohms. And X of C is 795.77 ohms. And X of L2 is 1256.6 ohms. So to calculate the total impedance then, we're going to have the 700 ohms of the resistor plus J times the 439.82 plus the 1256.6, that's the other inductor, minus the capacitor, 79.5.77. And so now notice here I'm keeping 5 significant digits. For each of these I'm using 5 significant digits to do the calculation. And so when so we'll get 700 plus J. And so looking here, right, we got 439 plus 1256, and then minus 795. So that's going to actually give us about 900 ohms of reactance. and if we take it all the way out to 5 digits, it'd actually be about 900.69. And again, the units for this is ohms. So this is the rectangular form. So this is the rectangular form of the impedance for the circuit. So remember, Z is the total impedance to the flow of current. Now, if we wanted to calculate the magnitude of that, you could do it using Pythagoras Theorem. So you could calculate the magnitude of Z, which, using Pythagoras Theorem, we have the real portion, and then we have the 90-degree phase shift, right? So we have 700. If I was to draw the impedance diagram of this, we would have R would be going this way. And then we would have X of L1. X of L1 was going up at 439. And then X of L2 was going up at 1256. I'm just kind of roughly drawing it here. And then X of C is going to be coming back down the other way, another coming down 795. And so then that would give us our overall resulting value. Okay. And so this would be our impedance Z, right? So here's our right triangle. So this is my overall impedance Z. And this is the phase angle. So using Pythagoras Theorem, we'd have the 700 squared plus the 900 squared, 900.69 technically squared, and then take that square root, and that would give us the absolute value. And then we could find the angle theta, which is this phase angle, which would be the arc sine, tangent, and we want to take the opposite, which is going to be 900.69 divided by the adjacent, which is 700, and that would give us the angle. Okay, and you could punch that into your calculator, but of course I like to use the Octave software. And so here you can see I've already calculated the Z in the rectangular form. But now what I want to do is calculate the polar form of that. And so I'm going to make use of the absolute value. So I'll take the absolute value of Z. And then I'm going to use the angle function to calculate the angle of Z. But the angle of Z, this function here, this function right here, angle of Z, gives me radians. So I have to change it to degrees. So I'm going to multiply it by 180 degrees and divide by pi radians to get my values. So now you can see that the overall polar value of that is alright, so the polar form of Z here, the polar form of Z is 1140.7 ohms, because remember impedances are in ohms, we're opposing current flow, the unit for that is ohms, with an angle of 52.146 degrees. Alright, so if I'm going to put this into Blackboard, okay, so this was the polar form of Z here. Now, if I'm going to put this into Blackboard, I'm going to put this in as 1.14 space kilo ohms. And you, if you're going to type it out, you would type HOMS. All right, or you can just find the omega symbol and copy that. Okay. And then at an angle of 52.1 degrees. So remember, if you're putting it into Blackboard, I need 3 digits. Okay, I need 3 digits, and I need a space here between the digits, the numeric value, and the units, including the prefix K for kilo ohms. All right, and so this would be the polar form that we would use to put this into Blackboard. Now, I do want to kind of point out to you here, remember back in DC circuits, we said that L total for a series circuit is equal to the first inductor plus the second inductor. Okay? And so when we look at the inductive reactance X of L is equal to X of L1 due to the first one plus X of L2. So these are just impedances, right? They're reactances, but they're impeding current flow, so they just add when they're in series. So even if I had like 2 capacitors, let's say I had a second capacitor over here. Well, the capacitors, call this one C1, right? Capacitors add in series, add as 1 over C1 plus 1 over C2. However, when I calculate the when I go about to calculate the capacitive reactance of that, right? Remember that the capacitive reactance already has the 1 over C in it, right? So the capacitive reactance is 1 over 2 pi times the frequency times the capacitance. And so it's already got this 1 over nature in it. So once I calculate, if I calculate like X of C1, that would be 1 over 2 pi FC1. And then if I calculated X of C2, that would be 1 over 2 pi FC2. And so we would actually end up simply adding those together. So X of C total for the series circuit is equal to X of C1 plus X of C2. All right. So because you're just adding impedances, and impedances in series add. Okay. But don't forget that there is the J term we got to keep track of. Okay. But that's how we could find the total impedance of a circuit like this. All right, so let's say that we actually are applying a sine wave supply voltage to this. So I have a voltage source here generating a sine wave, and I connect it up to this circuit. So we've calculated our total impedance of 700 ohms plus J 900 ohms. All right. But let's find out, what is the voltage drop across each element? So I've got the 4 elements here. What are my voltage drops? So to do that, we can calculate using Ohm's law. We could calculate the current. I is going to be our voltage divided by the total impedance. So let's just say that our supply voltage here is 100 volts RMS, okay, at an angle of 0 degrees. So this is the phasor or polar form of the voltage. And so using Ohm's law, we can then calculate what the current in the circuit is. Now remember, it's a series circuit, so whatever this current turns out to be, it's the same current through each element. And so we would take our 100 volts, angle 0, and divide by the 700 and plus J 900. 0.69, okay, and the units for that, of course, is ohms. And so we could flip over to our octave. And calculate that. So I'm going to say E is equal to 100. And now I can say I then is equal to E divided by, now I already have Z. You need to make sure you use a rectangular form here because that's the natural form for octave. So E divided by Z. Now E had an angle of 0 degrees, so I don't have to worry about no phase angle there. All right, so this is the rectangular form of our current, but we really don't want to see the rectangular form of the current. We want to see the magnitude and the phase angle. So we want the polar form of the current. And so again, we just go use this absolute value, but I for this time, and the angle I times 180 degrees divided by pi. And so this gives us our current, which turns out to be 87, almost 88 milliamperes, with an angle of minus 52 degrees, right? Because the angle of our voltage was 0, and we're dividing by the impedance, so the angle, you subtract off that angle, so you get this negative. So remember, Eli, the Iceman, all right? So when we look back at our circuit, when we look back at the circuit here, we see that the impedance, we have more reactance, we have more inductive reactance. Okay, we had 400 and some here and 1200 some here. So we had more inductive reactance than we did capacitive reactance. So the inductive reactance is really dominating in this circuit. So that gives us the Eli case. So the voltage has an angle of 0 degrees, and so the current is behind that, right? Eli says that the voltage is ahead of the current, or the current is behind the voltage in an inductive circuit. And so we would expect our current to be negative in this case. And so it is. So this is our values here. So let me just kind of record these over here. So the current is 664 milliamperes at an angle of minus 52.146 degrees. And again, I'm just carrying out all 5 digits for my individual calculations. So if I'm going to put it into Blackboard, the answer would be 87.7 space milliamperes at an angle of minus 52.1. So that would be the result that we would want to put in Blackboard. All right, so once we have that, then now we can calculate the voltage drops. So the voltage drop across the resistor, okay, again, it's Ohm's law, so it's I, this current here, I, times the resistance. There's no phase shift, so it's just that in there. So we just take the 700 ohms. So we're going to take the 700 ohms times this current and calculate the voltage VR. So using the octave here, I'm going to say like VR. So VR now is equal to the current I, and I'm going to use the rectangular form for my actual calculation, because it'll handle the complex numbers correctly, times R, which was just 700. And so that gives me the voltage VR, and I could calculate the polar form of that. I'll just recall this command. If you use the up arrow keys in the Octave software, you can recall the command. To get the polar form of that. All right, and so VR then is going to be the 61 61.365 volts at an angle minus 52 degrees. And so likewise, we could come over here and we could calculate, okay, all right, so we can calculate the voltage drop across the first inductor. Now I already have the I already calculated. Here was my inductor L1 and my inductor L2, and so I calculated those frequencies. So I actually have those already stored in the software here. So I can just say like VL1 is equal to I times XL1. All right, and that of course gives me the polar form, or the rectangular form, and so I'll just recall this and change the R's to L1. To get the polar form. Okay, so we've got VL1 is the 38.5 volts. All right, so VL1 is 38.5 something volts at an angle. Oops, I'm sorry, I messed that up. That's not correct because I'm missing my phase angle. Sorry, I need to make sure when you multiply this, that you also multiply it times your phase angle, J. Okay, so you need to make sure you multiply it times your phase angle, J, and then we can calculate the polar. I'm just going to highlight this and copy this. And so you see the magnitude actually didn't change, but the phase angle did change, and that's what was telling me that I knew I'd forgotten the phase angle because I was still at minus 52, and that cannot be correct. All right, so just take this, and this was VL1. Enlarge it a little bit. All right, so this was VL1. VL1. And then we can calculate VL2. Right, it's going to be done exactly the same way. Except we need to change the 1s to 2s. So we can just use the up arrow keys and recall the command and then calculate it. But remember, again, we do have to make sure we include the J, the phase shift of 90 degrees. And see, now that it's, this is the rectangular form of that. And so then if we go to the polar form, we just need to change the 1s to 2s. And make sure you don't miss any of them, or you'll be off a little bit. But this gives us the phase angle, and the magnitude, and I'll just enlarge that a little bit. Okay, so that's 110 volts at an angle of, again, this is a plus 37 degrees. All right, now I do want to point out something while we're looking at it. We only started out with 100 volts. And yet, VL2 is actually got 110 volts over it. Okay? So that is okay, because remember what we're doing here. The capacitor is getting charged up, and then it's dumping its charge. And the inductor is getting charged up, and the inductor is dumping its charge. So half the time the inductor is charging up, and half the time it's dumping its charge. And so when the inductor dumps its charge, it dumps it into the capacitor. And then when the capacitor charges up, when the capacitor is charged up and then it starts dumping its load back into the inductors. Now both inductors here. And so what happens is these inductors, both inductors here, are passing their charge into the capacitor. And then at the other half of the cycle, the capacitor is dumping it back out and sticking it back in the inductors. And so even though we only had a magnitude of 100 volts RMS coming in, right, we actually have 110 volt RMS across this inductor, and then we got another 38 volts across the, this is an L1 here, and inductor L1. Okay. All right, so now to calculate the capacitive, okay, again, it's going to be I times the impedance of the capacitor, which is minus J, don't forget the minus J, times the X of C. Okay. So I should have wrote it down for the other ones there, but there it is for that. So we're just, again, we'll pop over here. I'll use the up arrow keys to kind of, there it is, but this is just going to be VC times I times x of c times parentheses minus j, or I could have kind of did it a different way. All right, so I could also typed it in this way, and you'll see minus j times x of c. It's a little cleaner this way, but it gives the exact same result. All right, so now again, this is the rectangular form. So I'm going to recall this function to get it to just display it. This is just for display purposes, to display it in polar form. All right, so now we've got 69 volts, but notice this angle is minus 142. Okay, so that angle is minus 142. So let me paste that in there. So that's volts with an angle of minus 142 degrees. So notice this, if you take the 37 plus 37 degrees here, right, and you subtract that from this, you end up with 180 degrees. So your capacitor angle and your inductor angle are 180 degrees out of phase. Okay? And in a series circuit, that's always going to be true. They're 180 degrees out of phase, which means that when the inductors are dumping their load, they're charging it, they're throwing their load into the capacitor. And when the capacitor starts dumping its load, it's going to be dumping it into the inductors. They're 180 degrees out of phase. And that's how you can get more voltage, a bigger voltage drop across a reactive element such as the inductor or the capacitor. Okay, you can have a larger voltage drop across your reactive elements than your source. Now note, your resistance will never have a bigger drop because it doesn't have any energy stored in it, right? Resistors do not store energy. So the resistor, the voltage drop across any resistance or the combination of all the resistances will never be larger than the source voltage. But your inductors and your capacitors, you've actually have stored energy within them, and so that's why they may actually have a larger average voltage drop than the supply voltage, okay, because they've charged up, and then they're passing that charge back and forth between the inductor and the capacitor. All right, so here's our values for these voltages. So now remember, Kirchoff's voltage law, KVL, says that the sum of the voltages are equal to 0. Or to write it a different way, say that the sum of the voltage inputs are equal to the sum of all the voltage drops. Okay? Or voltage out, if you want to call it out. So the voltage supply is equal to all the voltage drops. So what does that mean? It means that our supply voltage E, okay, which remember it's a vector, our supply voltage E is equal to, and these are all vectors too, okay, is equal to VR plus VL1 plus VL2 plus VC. And so we can actually do that in the Octave software. Remember, if we add up these four voltages here, these 4 voltage drops across the 4 elements, we should end up with exactly 100. And so if we do that, okay, I guess I pulled it over here. So so if we come over here, I can actually go and take VR plus VL1 plus VL2 plus VC, and that gives me 100, right? This is 1.00 times the second power, so this is 100 at an angle of minus 7.1 degrees with minus, that's to the minus 15. So let's write that out. So the angle there is 0, it's a minus angle. All right, so it's minus 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 7, 1054. All right, so this angle is basically 0, right? So this is basically 0 degrees. Okay. And the magnitude is 100 times the second power, right? Or, I mean, excuse me, 1 times 10 to the second power, so it's 100, which was our supply voltage. So now the reason when you punch this in the calculator like this, or then the Octave software, and you don't get exactly 0, you don't get a perfect 0, it's just what we call round off error. It's due to the fact that we're basically dealing with irrational values. Remember that pi is in there, right? When you calculated x of L, right, and you calculated x of C, we use pi to calculate those, right? Right here's the equation for x of L, 2 times pi. And so these numbers are irrational numbers because they've got pi in them. And so you end up getting round off error when you do the calculations. But again, this, you know, if we take this to 3 significant digits, right, our answer would be 0.00. And by the way, if you're putting in the answer of 0.00, don't put in a negative sign, okay? Just put in a positive 0.00. All right, so that verifies Kirchoff's voltage law just using the calculator or the Octave software in this case to just add those together. All right, and I do just want to point out, right? It doesn't matter which one you add first, right? You could say let's take VC plus VL1 plus VR. The order doesn't matter. That's just normal mathematical properties. The order of them that you add them doesn't matter, which means that in this circuit I could switch around and put, you know, the resistor last, or the resistor in the middle, or the capacitor first, and it's not going to affect the overall circuit. All right, and again, actually, when you see it, when it was doing the math, you see that the angle did show up a little bit different. Instead of 7 to the minus 15, I ended up with 1.4 to the minus 14. But again, this is still 13 zeros in front of this, right? So it's 0.00, at least up to 13 zeros there, which is just 0. You know, there's no way you could even try to draw an angle this small. All right, so what I did here was I've got these phasors, and I actually have drawn these to scale. I used the Octave software to kind of make them look nice, and I've created some phasors drawn to the magnitude drawn to scale. So remember, E is right here. E is 100, Okay, so right, we have the voltage E was 100 volts, and then I've got the magnitudes of the rest of them listed here, right? VC was 69 at an angle of minus 142, and so on. So what I want to do is I want to also verify Kirchoff's voltage law by drawing a Phasor diagram. And so what we're going to do here is I'm going to take E, the supply voltage, and I'm just going to like drop this down. This is going to be my reference down here, and I'm going to start off down here a little bit, and so this is my reference. This is what E is equal to, and then we're going to add, or I'm going to, starting at this same point here, so starting at this point right here, let's see. Okay, so starting right here at this point, make that black, I guess. All right, so starting right here at this point, I'm going to start adding these other vectors, including the phase angles. So including their phase angles. Now, it really doesn't matter which one you want to add first. Okay, so let me go ahead and save this. And then what I'm going to do is we'll start off by adding the VL1 piece here. So I'm going to add this. So I'm going to copy this. I'm going to copy this phasor, or actually I guess I'll just cut it out of the way. Okay, so I'm going to, or just drag it out of the way here. But then I'm going to come up here and I'm going to rotate it. Now it says 37.8 degrees, and this software you can't do like 0.8 degrees, so I'm just going to estimate it by rounding up to 38. So I'm going to go to selection, and I'm going to rotate, and it's positive, so I'm rotating left. Oops, I guess I have to go to rotate, and then it's positive, so it's a counterclockwise angle, and that angle is going to be 38 degrees. Okay, so we're going to start from this point. So now I'm going to take this and I'm going to draw this, and I'm going to attach it right there at that point that E started. All right, and so we went up. So I've gone up here a magnitude of 38.5 in magnitude at a phase angle. So the phase angle here, just copy this phase angle right down here. So this phase angle is an angle of 37. It actually, when I rounded up to 38 degrees there. All right, so now let's go ahead and I'm going to do the voltage next. Okay, again, it doesn't matter which one you do next, but I'm going to grab the voltage across the resistor next. Now the voltage across the resistor is always in phase, so that's actually just going to go straight across like this. And then I'm going to add, again, we could do either one here, but I'm just going to go ahead and add, I'm sorry, the voltage across the resistor is always in phase with the current. Okay, but there is a phase angle here because the current is at an angle 0. Okay, so sorry about that. I kind of said that wrong. The voltage is in phase with the current through a resistor, but the current has an angle of minus 52 degrees in it. Okay, so I do need to apply an angle here because the current is at an angle, and it needs to be a clockwise angle because it's a negative angle, so that would mean that we're going in a clockwise direction, and I'm just going to call that 52 degrees. So that's just going to be 52 degrees. And so now you can see that that's like going down. So I'm going to have to scroll down here a little bit. And I'm going to tag that right on there. Okay, and I think it might be getting cut off a little bit here. So I'm just going to grab this whole piece here and raise it up a little bit. So, and re-grab my R. And selection, rotate, and clockwise 52 degrees. Okay, and so then that now is going down, and I'm going to tag that right on. So I got VL, so I'm doing VL plus VR. So now I'm way down here. Now, we can, you could add either one of these. It doesn't matter which one of these you want to do next, okay? But I think I'm going to have to make some more room, or I'm going to run out of room here, so I'm going to extend this down a little bit again. All right, so I'm going to come up here and I'm going to grab VC. So I'm going to add VC next. So I'm going to grab this, and VC is minus 142 degrees. Minus 142 degrees. So I'm going to rotate this, and so it's going to be in the clockwise direction. 142, should I round that up? No, just 142 degrees. Okay. All right, and so this is my VC. And so now I'm going to tag VC right there, and I did not quite make the image big enough. I need a little bit more room. I'm still running out of room here. Alright, so let me grab this again. So I'm going to tag this right on to the edge of VR. Alright, so now I'm way down here. So right, if you look here, right, we're actually way down here. Right, this is E, way up here is my source supply. And so, you know, we went up at this angle. And then here, this angle here was the angle of minus 52 degrees. So that was minus 52 degrees there. And then this angle right here is minus 142 degrees. Okay, minus 142 degrees there. All right, so now let me undo that so I clean up. So now what I need to do is, starting at this point, I need to add VL2. So I'm going to come up here and grab VL2. And VL2 is at an angle of 38 degrees. So I'm going to go selection, rotate. Now this is a positive, so that's counterclockwise, 38 degrees. And I'm going to tag that on right at the end of VC. So And you notice it's going the exact opposite direction that VC was going. But notice where it gets me, right? It gets me right here to E. So when you add VL plus VR plus VC plus the other VL, you get E. That is Kirchoff's voltage law. So this is the graphical representation, also known as a phasor diagram. So this is a phasor diagram of the voltages. So we have our supply voltage E, which had an angle of 0. And so it started right here and just comes over here. And then we added VL1, then we added VR, then we added VC, then we added VL2, and lo and behold, Kirchoff's voltage law works, and we're back to 0. Okay? And so this is our phasor diagram. This is the phasor diagram for this circuit here when we apply 100 volts with an angle of 0 degrees to it.